Okay, so probably we can start today's session. Okay, so this is your week 5 tutorial session. So, so today, uh, in this session, we'll be mostly discussing on quantum information. So it's basically the background of the quantum foundations topics that we'll go through, and yeah, of course, even this week has been dedicated uh, on these topics mostly, and also like a few topics been introduced in last week's lecture series. So so yeah, I've been looking into this week's assignments. Most of the questions are covered from this background. So hopefully, like people can uh, find them. I mean, in your NPTEL portal. If you are not updated, then just go through the I mean lecture series, what has been done and what has been uploaded on your NPTEL portal, and just then follow them as soon as possible. It's already week 5 for you, so 3 more weeks, and then this would be done for your advanced quantum mechanics course. So, uh, so yeah, we'll discuss some important aspects of this quantum information, starting with entanglement. So, yeah. So, so like we know that like this is a very popular term, at least in the scientific community, or even outside, like quantum entanglement is something very much that people come across, and even modern technologies tries to use this phenomenon, this exceptional phenomenon of quantum uh, laws, I mean, which is, I mean, uh, I mean, which is really astonishing that it has many incredible consequences in terms of technological developments, and also other uh, like like technical developments in other areas of research, and yeah, and modern science. So now like from a basic point of view, we'll try to see like from the mathematical picture, like how and like what is quantum entanglement is basically all about. And yeah, so it is a property of two or more quantum systems, where uh, H1 and H2 are some two Hilbert spaces are associated with each other. So, like we talk about this entanglement property when two or more quantum systems are taken together, or are associated with each other. It's basically what you say. Like you have a very, I mean, you have a complete, you have a principal quantum mechanical system, and within it you find two or more subsystems, and those each of those subsystems corresponds to a particular corresponds to their respective Hilbert spaces H1, H2, and so on. So suppose if we have a quantum system which is described by Hilbert space H1 and H2, then the complete Hilbert space, or which is a composite Hilbert space will be given by H1 uh, tensor product with H2. So, that is how we see. Normally, even in the case of, for example, let's say like qubit systems, or yeah, very commonly we deal with qubit systems, which are nothing but the spin-off systems that we are very familiar. Like even in this course that we have talked about a lot about this spin-off system since the starting of the topic of spin and momentum, and we have seen like spin-off systems are something uh, like I mean very interesting. Like if you would see from this from the perspective of quantum information, those spin-offs are treated as some qubits. So like in spin-off system we uh, take uh, this state as the this is the eigenstate corresponding to the S state operator. If you remember, like we have seen over and over again. So this is something we denoted by upstate, and this is which we denoted by downstate. So these are spin-off states corresponding to the eigenstates of sigma z uh, operator, or the spin angular momentum of z component. I mean the operator which you have, and its eigenstates are basically given by this 1 0 and 0 1. So if you consider this system, and let's say you have two such systems, like this is corresponding to one, and then you have another spin-off system similar to it. You would have something like this, which I'm denoting with substrate 2, and so in that case, your total Hamiltonian system will be the tensor product of these Hamiltonians. I mean, you have two sub Hamiltonians, like one corresponding to spin one, which is spin half. I mean, we are labeling it, or denoting it with the subscript one, and then the other subsystem which we are denoting with the subscript 2, that is again another spin-off system. And when you study them, you take the tensor product of their respective Hilbert spaces, and also then you study the total like configuration. When you study the overall configuration, we consider like for example, in spin-off states we see two spin-off states are generally uh, given by this. Uh, so yeah, and also its linear combinations. So these are the like configurations that we get when we involve two or more like quantum subsystems. So like so this comes from the quantum subsystem 1, this comes from quantum subsystem 2, similarly here. So or in general you denote this as something this. So that is the way how we denote a state for a composite system, and that composite quantum system itself is made of two or more subsystems. So that like that is the very simplest example of a of two spin-off systems are associated with each other. Like I hope you have gone through them in the past very well. So that is what something which we are going to harness this that very basic idea over and over again in this session. That is what very important for the uh, to understand, various wonderful foundation applications and basics. So yeah, so that is how we write. So a state of the combined system is something written like this: psi 1 and psi 2, just like how I showed you right here. So this state can be written as the tensor product of upstate of the quantum system 1, tensor product with the upstate with the quantum system 2. So it's the same, like we can write any arbitrary quantum state of a composite system like the psi one tensor product with psi two. So, however, to understand entanglement, we need such kind of systems for sure. But the underlying idea is the state of the that combines system. Uh, I mean, you cannot say a given quantum state psi uh, if it is expressed something as psi 1 tensor product psi 2 as entangled state. What I mean, like this psi, this state, uh, um, this state is not, this is not an entangled state. This is something, the very basic, I mean, the uh, most important thing to note about before knowing what is entangled state. So, what is exactly entangled state is given following. For example, if you have a qubit system, just what I was referring to here as spin-arm system. So that spin-arm system, in the language of quantum information, we call it as qubits, and we'll see like that is what the primary source of the entire quantum information or quantum computation. So in qubit system, this is not entangled if we have like, uh, for example, this comes from your state quantum system 1, quantum subsystem 1, and this comes from the quantum subsystem 2, and the total state which we denoted by some composite state sign is not uh, uh, is not an entangled state, uh, but if you take linear combination of these composite states, that is this is given right here. So then in that case, this is an entangled state. So uh, this side is basically this can be yeah, this is your entangled state. So entangled state, and this particular exactly this state is something which we also know by as EPR state. So uh, or we denote it as criteria, and that's one of the way to denote. I mean, this is one of the like there is uh, quite a big story about it. How this is something like turned out to be a very I mean, turned out to take a very special name as EPR state. EPR goes by the names of Einstein, Podolsky, and Rosen, and it is them who first like proposed I mean it is first who then like proposed the EPR paradox, or like it's basically I mean the I mean, they were not really happy about how things works in quantum mechanics. They felt something strange about it, especially the idea of entanglement, and they come up with something very, very, constructive alternative of it, which they called out as something as hidden variable theory. So, but that hidden variable theory could not stand against this idea of quantum entanglement, because quantum mechanics, how they inherently work, is very much, different from the hidden variable theory, which basically uh, like comes from a classical idea. So we know like the classical idea like breaks down completely when we are talking about quantum systems and quantum phenomena like entanglement, and this is something was later like proved by Bell. So uh, yeah, hello. So Mehdi, could you able to give me?
Yes, yes, yes.
Yeah. So
Okay.
I have already like gone through like because it was
Okay.
already over the time. So
Okay. No problem.
I mean I've been done it quite a lot, but I was just starting right here about talking about the idea of entanglement.
Okay.
So if you want, like I can quickly go through.
Okay. Just give me some short,
Yeah, sure.
short.
Okay, okay.
Okay. Thank you.
Yeah. So I was telling about this entanglement. So today's, topic is about quantum information. So because this is something introduced in your last week's lecture series, and also even in this week some topics are more like continuing further. So and of course your assignments are again based on this topic. So it's better to start this important aspects of quantum information on uh, this. On this evenings of problem solving session. So I started with the basic phenomena of quantum information, the prime idea that is one of the uh, big phenomena of quantum information is this entanglement, which is very popular, that you always hear about them like in various contexts. So here I was just particularly like giving a mathematical picture of what quantum entanglement is and how we understand them and its applications. So to understand this quantum entanglement in a complete in a better mathematical picture, so can uh, what you can do is basically, so you consider a composite quantum system. So by composite quantum system, I mean a quantum system which is itself made of two or more subsystems, two or more quantum subsystems. So for example, you know about spin-off systems. So in spin-off systems, like this is what I was talking about. So um, in spin-off systems, like you have upstate and downstate, which are given by 1 0 and 0 1. So this is what something we've been talking about this in last few weeks, and also something which has been talked a lot about in your in this NPTEL course, that it has been started from spin angular momentum. If you would see, like it's the spin-off algebra that has been used a lot in various places in various other topics. So this is something will become the starting point here also. Like the basic tools which we would be carrying further for our discussion for the rest of the session this evening. So like in spin-off system, like we have upstate and downstate. These are basically the eigenstates corresponding to the uh, SZ operator. So if you remember SZ operator, the spin angular momentum of the Z component. So this 1 0 and 0 1 are basically the eigenstates of states of SZ. Similarly, you have eigenstates for Sx and Xy. So, but we always start with SZ operator as something, a very familiar convention which we are treating. That is, let's say we have two such spin half system. So let's say upstate one and downstate one, and similarly you have um, uh, upstate two and downstate two. So then when you combine the system, so basically you take the tensor product, or let's say this H1 corresponds to spin half um, spin half system 1, and this corresponds to spin half system 2. So this H1 H2 are the Hilbert spaces. So when you combine them, you will get a bigger Hilbert space, like which is given by the tensor product of both these Hilbert spaces. So even in this Hilbert space, when you define a state, so like that is basically you have read in the part of addition of two spin halves or more uh, spin-off particles, like what you
Correct.
do. Yeah,
So tensor product basically means that
yeah.
in the Hilbert space, the operator will act only on a particular subspace. It will not affect the another subspace.
Right. If you are generally we take whatever operation which we will do on this Hilbert space, we will be specifically we will take this concern like which operator we are taking, and like for example, let's say we will also see this in the
Okay.
upcoming discussion. Like if
Okay.
you are taking your operator something sigma x one uh, cross sigma x2. So this is an operator which will act on both the subsystem.
Yes.
And if I am taking particularly of something sigma x1, then it will only act on one of the subsystem of this Hilbert space. So sigma x1 is operator. I have to act this on a state. So state would be something psi, like psi1 cross psi2. So if I am taking psi x1, sorry, if I'm taking sigma x1 as my operator, then if I want to act on this sigma, sorry, if I want to act on this psi, then it will only act on psi 1, not on psi 2. But if I take this one, it will act on both of them. So, so this is something we'll take care of within the coming discussion of this, uh, like, I mean, this discussion.
Okay.
Right. So,
Okay.
that was your question, right?
Yes. 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 Okay. Thank you.
Okay. So yeah, that is what I was trying to tell you, like how we explain this entangled states. So if we have a composite system, then its state would be defined by psi equals to psi one tensor product with psi two. So so for example, but one thing to be noted, to understand quantum entanglement, we of course need this. A bigger system, a composite system made of two or more subsystem. But if its state is expressed something like this, tensor product of psi 1 and psi 2, then that is not an entangled state. So something you have to note it very well. This is not an entangled state. But what is an entangled state? Let's see by through an example of qubit system. So qubit system are nothing again but the spin-off systems. So in the language of quantum information, we refer to as qubits, and yeah, and that is what the starting point of all your quantum computation and many more things which you particularly deal with quantum information. So uh, right here, if I'm having a qubit system, so in qubit system we have for each spin-off system. So here again we are dealing with two spin-off system. So for one spin-off system we are having two eigenstates of sz operator, so upstate and downstate. Similarly, we will have another spin-off system. That is what we are denoting by subscript 1 and 2 here. So if a state is expressed as something psi, then its tensor product would be uh, uh, the psi. Then if that state is something as upstate 1, tensor product with downstate 2, which is otherwise denoted like this: up down, the get of up down, that is the notation to this composite state. Then that is not an entangled state, something which should which we should remind ourselves. But what is an entangled state? If we take such kind of composite states in linear combinations, that is given following right here. So psi, when it is given like this, tensor product of upstate of the subsystem 1 and with the downstate of the subsystem 2, and so on, so forth, then that is your entangled state. If you express this product states, this is a product state. Let me make it clear. This is a product state, and this is a linear combination state. So linear combination state of product states. So when you write a linear combination of product states, then basically you can have a entangled pair or an entangled system. And for particularly this this state which I am denoting right here, that is uh, like something even called by this EPR state. So where EPR stands for Einstein Podolsky Rosen. So like before you were coming, like I was talking about this exact this EPR thing. So EPR is something bit important. So which I'm not going right here. Otherwise, like it would take a lot of time to discuss this. So, but it is a very interesting and very important thing. So, I like suggest you to go and check out like what it tells us about the about the idea of quantum foundation. Like it has, yeah, this is on about like Einstein Podolsky Rosen paradox, so which we call it by EPI paradox. So like they proposed an idea, an alternative idea to this to the I mean an alternative idea to understand the picture of this quantum phenomena, particularly this quantum entanglement, where they proposed the idea of hidden variable theory. So, but later it was proved by another scientist, John Bell. So, where I mean, well, that guy, John Bell, actually tried to prove the theory of Einstein's hidden variable theory, and along with, I mean, the Einstein Podolsky Rosen, which they proposed the theory of hidden variable theory, that has been tested by John Bell, which found out that 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 doesn't stands as we understand quantum mechanics, because hidden variable theory is something to do with a classical picture, and classical picture completely breaks down when you are talking about quantum phenomena. So that really won't fit in exactly how Einstein, Podolsky, and Rosen wanted to see this happening. So this is a very interesting story behind. You can go through and check out. Like that is something you should do. That that will give you, very interesting idea about how to understand things using hidden variables. Is it really necessary that we uh, uh, really need something other, which is called by hidden variable theory, to understand quantum entanglement and other things in quantum mechanics. So that is something for a later thing which you can check out. But now, what I was talking about here. So we can quickly see, as I was telling about quantum entanglement. Uh, so mathematically, how you write a quantum entangled state, that is, you write as a linear combination of product state, which I was showing you right here. So if you will see, taking that idea, you can check out some problems right here, some quick questions on it. You have to check whether the given states, psi 1, psi 2, psi 3, and psi 4 are entangled states or not. So, so if you start from the first bit, that is psi 1 is given as uh, uh, 1 root 1 by root 2 of tensor product of upstate. Let's say this is from subsystem 1, this is from subsystem 2, and again, or let me denote something else like A and B, and B. Then in that case, whether this state is entangled or not. So you can see that this clearly looks like a linear combination of product states. So you have a product state, what are the possible product states? So these are your possible product states. uh, and so on. So, and when we are taking a linear combination of them, and further you can see if is there any way that you can factorize into some other state, like something like if you cannot decompose, or if you cannot uh, express this linear combination of this tensor product states into something as phi 1 and phi 2, which is basically which basically boils down to a product state once again, uh, then that state is a entanglement state. I mean, if you cannot do this, if you cannot uh, express this linear combination state, entire state, into some tensor product of phi 1 cross phi 2, then that is a entangled state, because since this is the only form, the expression which is given here for psi 1, uh, uh, like uh, let me write a code on it, like psi 1 uh, is an entangled state since it cannot be re re-expressed as some product of tensor, as some tensor product state. That is uh, psi 1 cannot be written something as phi 1 tensor product with phi 2. But now, if you go with the second one, psi 2, well, can you see this as some kind of entangled state? Uh, like this looks like linear combination, but you have to be careful that on a like a careful note, this is something which you can write uh, side 2 is given as yeah. Someone has to say something. Okay, so
No, nothing, sir.
okay. So if I write the state uh, one second right here, so what is upstate and separate with down plus uh, downstate and separate with down. So this is something I can write it as upstate plus tensor product. This is what I can write, and you will see we denote this state as something this, and you see like psi 2, I'm able to express something psi 2 uh, as some tensor product state. So if psi 2 is some product state, like as I said, then this is uh, not an entangled state, not an entangled state. So like same way, like you can check for others as well. So uh, psi 3 is uh, this one. If you would check again, like there is no way you can uh, break this, or like reduce it to a uh, so this is abstract. Yeah, again, if you would see this psi 3 state, this is something which cannot be further reduced to a product state, and hence this is the final form of your composite state psi 3, which is expressed as some linear combination of tensor product states of its subsystems, then thus this is a entangled state.
Hello.
Yeah.
So inside two,
Huh.
uh, how you write the superposition of omega root over 2 spin up plus spin down as this kind of notation is this? What does it mean?
So you are telling me like this side two, like I'm writing this.
No, I understand that it should be finally it should cannot be expressed in a product state, right? The
Finally, the side two can be expressed as a product
as a
state.
product, but it should be written in the form of a linear combination. That's why it is not an integral state. But this notation,
Huh.
that
Uh,
third line, the notation is
Side two.
1 over root over 2 spin up plus spin down. If you
This one.
write this notation in this way,
This
what
one.
does
You're talking about
yes,
this one.
yes, yes, it is okay. Then the third line,
Third line. I mean,
this notation, the first one.
it's that right arrow you're talking about.
Yeah, right, right, right.
Oh, so you're telling like, so this is this notation. Like, yeah, what happened with this notation?
Uh, Actually, what does it means?
So
You can write.
I mean, like, okay, so I can tell you like this simply means this state. Uh,
Okay, so it has nothing to do with polarization or something, left or right polarization, nothing.
uh, yeah, if you're talking about in the language of quantum optics, then uh, like this state has a meaning, and further if you want to know, I mean, we are just doing a general discussion. So
Okay, okay, okay.
this state basically denotes your eigenstate corresponding to the Sx operator. So you remember like
Okay.
Sx, like or basically like the sigma x operator, which we learning about the spin angular momentum, the spin algebra previously. So the states which we are working right now corresponds to this Sz operator, the eigenstate of Sz operator. So this eigenstates are this. Similarly, if you would see the eigenstates for Sx, then that is this,
Okay. Now understood.
where this a right arrow state can be expressed in terms of linear combination of eigenstates of Sz operator. So this belongs to the I mean the eigenstate corresponding to the Sx operator,
S6 operator.
and these are
Hmm.
Sz.
Okay, thank you.
So now, if you take the difference between the up and down state, then that will become your this state. That is just notation. I mean,
Okay,
like we denote it by like this. So that, and that is again your second eigenstate corresponding to your Sx operator. So
okay. Thank you.
but if you, yeah, as you were telling, like you want to see them as some form of polarized and so on, like you can see them in the context of quantum optics, there is there are this like quantum states which we denote as some polarized states, like circular polarized or like some left polarized, right polarized. So we, like if you talk about in that context, like we'll discuss them, but since we are doing something general,
Okay.
so right now we cannot specify them, like what polarization will exactly mean here. So
So now it is just the state of S6 operator.
yeah.
Okay.
Sir, can you again explain how to find the
Sorry,
entangled state? Sir, no?
sorry, I couldn't hear you. Could you tell me again?
Hello?
uh,
You're able to
yeah, yeah, yeah.
hear me? Hello? Sir, can you just explain again how to find the entangled states?
So you are telling me like to explain this again, like how we were doing this.
Yeah, yeah, I was missed it first.
Okay, so shall I start from the first bit, or like where exactly you want me to?
First one is sufficient.
Sorry, could you tell me like where exactly I have to start?
Uh, can you start? with first one
First
once.
first problem, no,
I will
bit one.
catch it later. Yes.
Okay, yeah, yeah. So what I was telling, like for a, let me just a minute. Let me fix the headphone. Yeah. So I was telling what is entangled state, like how we mathematically express them. So if you are expressing some state as like this psi, like that is the product state, that is a tensor product state of up state with the down state. So this is from your Hilbert space 1, and this is from your Hilbert space 2. That is what I was showing you right here at the beginning. So if you are expressing some uh, state as some form of tensor product state, like for example, I have shown them here. Yeah, I mean, uh, like for a spin-off system, we write something as this spin up, or we denote it as this way. So this is not an entangled state. Uh, I hope you are familiar with this kind of states. Like when we take two spin-off particles and when we try to combine them, when we see the addition of two spin angular momentums, then what happens to the resultant state? Like there are various possible outcomes that we'll get, like spin up and spin down. So but if you particularly see this state, like which is spin up tensor product with spin up, so this the first spin up comes from first spin up particle from the Hilbert space of first spin half, and the second comes from the second spin half. So but when you write them as some tensor product state, then that is not an entangled state. But what is an entangled state? When you uh, write them as some linear combination of these tensor product states, like this. So that is your entangled state. So if you see like psi 1, that is written as some linear combination of tensor product states. This cannot be reduced to a some kind of uh, product state. It is a like you will see, that is this is the final form of the expression for the state psi 1, which is only expressed by some linear combination of product states, uh, up down plus down up. But if you see for the second case, for the second problem, side 2, uh, this is written as something again, some linear combination of product states, up down plus down down. But if you see carefully, this can be reduced to some kind of phi 1, phi 2 product state. That is, I have written here. So this is your psi 2, and this I too I have again rewritten as something, this some I have I have like broken this apart, like where this I have taken a overall common state, that is the down state, uh, on the right of the tensor product. So and whatever is left on your left, that will be some other state which I am denoting as right arrow state, that is given as this. uh, so yeah, so that is uh, given here. So and you see, like I can write this side 2 as some form of this state. Then this is again a tensor product state. Then that means I cannot, this is a product state, so that means I cannot call it as a entangled state. So this is not your entangled state. So that I was telling. And again in bit 3, you will see that you cannot again uh, you cannot reduce to some phi 1 phi 2 form. uh, this is your final form of your state 3. So then if it is a final form, you can see it is a linear combination of product states, two product states. It can be more than two product states as well. So uh, therefore this is an entangled state. So is it now clear for you?
Yes, sir. It's clear.
Okay. So if anything, any problem, you can. So yeah. Uh, then we have the last one. Uh, so last we have uh, psi 4 is 1 over 2. Uh, plus- so this is your psi 4 state. So and here you can see, like, is there a way that you can convert this out uh, into some kind of phi 1 and phi 2? Well, if you see, even again you will carefully examine, uh, so you will find out, like, this is your basically, like, you can check them out. This is basically your tensor product state of these two, where uh, yeah,
Hello.
yeah,
The third term in the psi4 it should be a kate, yeah, not bra.
uh, which one?
The third one
Uh,
in
th-
psi4
Sai.
it should be a kate, not a bra.
Oh,
Spin
sorry,
down.
sorry, sorry. Yeah, yeah. Thanks. Yeah, yeah. This is this is your state. So what I was telling, like, you can, if you would carefully examine this, like, you can build two such kind of linear combination of state. One is this one, which I earlier showed you right here, and other again, taking that same linear combination with the negative sign, you will get this one. Uh, you just take a negative sign uh, from the, like, there is a, here you have a relative sign between these two up and down states. Earlier you do not have them, which you denoted as some right arrow state, and now you are denoting as some left arrow state. So if you see this entire expression can be written as a product of right left states. So this like becomes a product state. So that means this is not an entangled state. So like, I hope, like, you understand how we see entangled states and non-entangled states. Like, so this is like how you mathematically define them in terms of a quantum state. So at least this idea is clear. uh,
Hello.
yeah.
It is not clear, but you can have a say multiple of states of many particular states. Yeah,
Yeah, yeah, yeah,
not
yeah,
only two particular
yeah,
states. You
yeah,
can
yeah,
have three,
yeah,
four,
yeah,
n.
yeah,
Okay.
yeah. So like, for example, I mean, there is this state called GH, like, one, as I said you, like, there is this EPR state, which goes by the name of instant photosclerosation. I mean, Rosen. Uh, that is denoted something like this, which I, like, showed you at the beginning, like this EPR state. Sorry, like, This will be up, up, and down. Similarly, you have this GHZ state, uh, which uh, is something given like this. So even this is something like you would see sometime later, but like mostly today we'll be working with the CPR state. So that is very common, like entangled pair of state, like which you also normally get in almost in every case. Like when, like if you see some kind of entangled state, say let's say, I mean in like in particle physics, like when a muon particle decays into some two pion particles, like we call it as those pion particles which was emitted from the muon decay. That is itself, those pion particles exist in terms of some entangled state, and that is again given by, if you would see the state of that, those pion particles will be denoted by this EPR state. So yeah, like most commonly we see with subsystems, but like as you were telling, like we can study this entanglement system for one or more subsystem. Like by composite system, I don't mean only two subsystem, but more than two it can be possible. But for simplicity, we're keeping with two.
Sir, I had a question.
Yeah.
Like, there is a property for entangled states that if we measure one particle, it will affect the
Sorry.
other. Hello,
Uh,
you're able to hear me?
yeah, yeah, yeah. You can tell.
Like there is a fact that if we measure one particle, it will affect another particle due to entanglement.
Huh, huh.
So here, can you mathematically
Uh,
explain me how
so,
one state affect other?
like you are telling, like upon measurement of one particle, like the other particle state would be collapsed. Like you are talking about that.
Yeah, like here we can do any operation on this
Yeah, yeah,
wave
yeah.
function and see.
Yeah, you can, I mean, we'll see like some of those examples, this is what entangled states are all about. Like when we like as I was talking about the example of pion decay, like if two particles are entangled, like if we are measuring the state of one, then automatically the state of the other particle will be collapsed. So like that state is the I mean other particle state is also determined exactly at the same place, uh, I mean exactly at the same time. So like we can that is a like one of the important feature. uh, yeah, so yeah, we can do that. Like, is there something more you wanted to?
No, nothing. Like mathematically, we can measure on this by changing some operation of this function. Like that
Oh,
also we can
you
do.
are telling, yeah, you can do that. Like for example, like if I'm taking let's say, I mean, uh, uh, yeah, for example, if I'm taking the EPR state, or let's say some other linear combination of state, which I was earlier showing you right here. Let's say state one. So this one right here. So if I operate with, let's say, sigma z. Okay, so if I operate sigma z, and let me say I'm operating sigma z for system A. So let me denote this as A. So I'm operating sigma z A on psi 1. Then you will see that this will uh, uh, like uh, like this will the it will that will give you something. upstate, downstate with some overall factor, uh, uh, not exactly this one. uh, Let me, sigma z when you operate downstate with uh, 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 like I have to think this like again, like for example, sigma z a won't be like telling you how exactly, uh, because this entangled state is again in some linear combination, but like for example, uh, this entangled state is not in given uh, a particular eigenstate, like it is a linear combination, so you have to choose a operator such that it will like collapse into a like a single state. If it collapse into a single state, then which state we can think of right here, uh, like for example, I mean, like you have to. What I'm telling, if you operate sigma z a, then you will get sigma z a on psi one. You will get some states. Let's say some psi two, and then when you operate sigma z b on psi 2, like it will give you the counter state of the result which you got for psi 2. So I mean that is how, you can see that. I mean that is how like entangled states are.
Okay.
So like we will see some of the examples, like we'll talk about some dense coding and this I mean quantum teleportation. So where this kind of things will be there, so we'll talk about it. So okay, so is there anything more you want to ask?
No, nothing.
Okay. So the first thing like we can know about this uh, entanglement, like the like one of the important application which we can know, is this dense coding. So what is this dense coding is like, we know, like we have come across this news very often that like this using this qubits and this qubit systems, like we can able to construct like modern quantum computing technologies which are really more efficient and faster than the ordinary classical computers. So one of this reason is like by the like harnessing the idea of this quantum entanglement. This makes everything's efficient. Like for example, one of the application that we see is dense coding. What we do here is like, I mean, we can able to transfer some classical information through qubits, and this is like not just some like for example, you have a one classical bit, then it can transmute. If you want to send this bit of information to someone, like it only will carry only one bit of information. So like for example, a classical bit is denoted by something 1 and 0. So like let's say 1 denotes something yes, and 0 denotes something no. Then this a single classical bit will carry either 1 or either 0. But if you use entangled qubits, then it can hold both of this information in a single qubit. it has to be, and you have to note that it has to be entangled. Like a not just if you have just simply a single qubit, like it will give you a same information what a classical bit would do. Like it can be zero, like a single upstate. That is what qubit is. It can like give you it can carry information which is encoded as zero, or let's say some downstate, that is another qubit. It can again encode one bit of classical information, that is one. But if you have a something entangled qubit, it can carry both zero plus one, or one plus zero, more than one classical bits you can transfer. So that is what the one of the significant uh, application that you see in uh, I mean in this uh, quantum entanglement. So for example, like here uh, I have a qubit, and this is an entangled qubit, uh, entangled, and you will see that this qubit can hold more than one classical bit, like it. Classical bits, so it can hold either 1 1 or 0 1 or 1 0 or 0 0. So like how it does, like we can see that let's say like we will start with this the same APR entangled state, which is denoted as chi minus. uh, um, let's say there are two-person, uh, uh, Alice and Bob. I'm denoting Alice as, and Bob as B, and Alice wants to send information to B. So basically, she wants to transmit informations. She basically wants to send a message to Bob in the form of some classical bits, but using entangled qubit. So, uh, so like. Uh, that like how we can see this, like for example, if I um, start so yeah. So for example, like Alice, so as I told you, Alice wants to let me so Alice wants to communicate with Bob. Like she wants to send a message, send some classical bits of message to Bob using some entangled pair. So let's say, and you will see the entangled pair. It need, as I told you, it can be any linear combination of product states. So one of this is APR state. So this EPS state, but it is not the lone entangled state. Like there can be other possible ways to have entangled state. One would be this and this and this. So uh, uh, yeah. So these are other ways of the of having an entangled system, of having this is the possible ways of having an entangled state when you are using two qubits in the in the sense that you are using two spin-off states. So using two spin-off states, like these are the possible entangled pairs you can have. So chi minus, chi plus, phi minus, phi plus. So if we start with chi minus, and let's say like what happens if Alice wants to send some message to Bob, then using this entangled pair, then she first has to know like which entangled pair she is having, because like when you have a quantum state, you won't have any idea about that quantum state unless you measure it. So even Alice doesn't have any idea about this state. So let's say Alice, for if we assume that Alice has this chi minus state, and if she measures sigma, the first thing is, if she like the first step is she doesn't uh, doesn't uh, measures anything. The uh, second option would be she measures, let's say Alice measures sigma x, or basically x sigma x. Then you would see when you act sigma x on chi minus, it will give you sigma x on chi minus. And remember, like when I'm writing sigma x is measured by Alice, that means it will only act on the A state of the entangled pair. So here A denotes Alice and B denotes Poe. So this this is a entangled state, like among the quantum state that is in position with Alice and Bob. So if Alice is measuring sigma x, then that means uh, sigma x tensor product, some identity operator A and B is acting on chi minus. That means if you operate uh, this will give you sigma x A tensor product with uh, not this one, cross identity operator B minus sigma x A. So this is what you will get, and you will see that when sigma x operates on the upstate, so sigma x basically, let me remind you, like this is something given by this. If this acts on the upstate, then that will give you like downstate. So that is uh, 1 by root 2 downstate. That means this will be down and down. When identity operates on down, it will be down. So this is A, so A B. Then again, when sigma x x on downstate, it gives you upstate. So that is uh, upstate tensor product with the identity operator acting on the upstate. So that is again identity operator. So this is something we can write it as minus of. I'm just taking a negative, overall negative sign, or overall negative factor. So that is given as 5 5 minus. So that is this step. So when uh, like if we assume that like Alice is having a initially Alice has this entangled pair that is chi minus, and when she measures sigma x, then she is getting phi minus. So similarly, if you do the same way, if you would repeat this exercise, if she Alice x sigma y, then like this uh, sigma y on EPR, or basically I'm denoting it by chi minus. That will give you uh, minus I phi plus. So again, you do the same exercise. Here, sigma y is, let me remind, this is your sigma y. And when L is x, sigma z, then you will have sigma z x on uh, chi minus. Then uh, this will give you chi plus. So yeah, so this will give you chi plus, and uh, yeah. So right now, before one of you were asking me about how we can like get the I mean, if one measures the one pair of the entangled state, then we also able to know the the other I mean the other half of the state. So that is can be seen from here as well. Like when I'm operating sigma z, like in this chi minus, it is giving me chi plus, and chi plus is this. So if this chi plus is this, then you can see that uh, hello, hello, my voice is audible.
Now audible, but before sometimes it was not audible. Now it is okay.
Now it is okay.
So I I
Right.
have a question.
Yeah, yeah.
It is not quite clear, but you are saying that if you know, I am asking this from my some question is that
Uh,
you said that the transformation is between Alice and Bob.
uh.
So you have some quantum states. So if you operate some, say for example, you said that Alice operates sigma A, sigma or sigma Z, whatever it is,
Mhm.
and then you can get the other entangled states by the
Yeah,
operation of
yeah,
Alice.
yeah, yeah, right.
That means that can I think like this way that you have some entangled states in the nature, say it is naturally there.
Uh,
Now
uh,
when you are measuring, then you know other entangled states. There's something like some hidden variable that means it.
uh,
These are the hidden state. When you
no.
measure, then you know.
You're telling these entangled states are not exactly entangled. They there exists some hidden variable by virtue of that, like they are becoming entangled. You are telling that
So I'm saying that in nature,
in nature, right?
you I'm saying about the preparation of the state.
Yeah.
Do you prefer this entangled state or it
Uh,
is already in nature in the superposition, linear superposition in entangled way?
uh, so we there are various sources to get this entangled states. Like one of the example which I was telling you, like when you have this I mean muon decay, that in particle physics you will see, it gives you a pair of pion particles which are basically entangled. They are entangled by nature because they have to be entangled. There are various reasons to it. They have to conserve angular momentum and so on. Those are the underlying things which ultimately or eventually makes your resultant pion particles to be entangled. And same way, like you can also see when you pass photons through a beam splitter, it gives you two different polarized photons, and that is further again, those two photons are entangled, and you will see their quantum states that would be something represented either of these four states. If those photons could be treated as some kind of qubits, then yeah, so in nature you see them entangled, if they are some spin-off particle, or if they have something some familiar behavior of or qubits. I mean, if they have a spin-off type nature, then it has to be either of these four types of entangled pair.
Okay, thank you.
So there are entangled pairs which comes very naturally. Like in nature you can see them. There is no hidden variables to it. Like that is again which I was telling you like minutes before. Something what Einstein, Podolsky, Rosen, they also proposed that idea of hidden variable theory. Like there can be something more which we are unable to access it, or which we cannot grasp it. But you can eventually see why that entanglement is happening. That is through some hidden variables. But that claim was disapproved by John Bell, like another famous physicist who mathematically showed he devised a theorem or in mathematical inequality. Through that he proved there doesn't exist any such hidden variable thing. Quantum mechanically, in quantum mechanics you see this entanglement inherently.
Okay.
So yeah, yeah, like even now, yeah. So like I was talking about this teleportation. So like as I said, if we would assume that Alice has this entangled pair, then if she measures sigma x, sigma y, or sigma z, then these are the four possible outcomes she can have. Then and then again, if like after her measurement, if Bob measures, let's say now, uh, Bob measures his part of the state, his like the entangled pair of the state, then and this time uh, the Bob has to measure mm, following. Uh, Bob has to measure through this following and sigma z, sigma z. So if Bob measures right now, then let's say if Bob measures this on uh, sigma x cos sigma x uh, on 5 plus, like that is something the next exercise is also. So maybe we can see directly here uh, what I can see. Bob measures sigma x cos sigma x on 5 plus. Uh, so again, you can uh, do the same exercise which we started with 1 by root 2, 1 over root 2, and your 5 plus is this one, up plus down down. Uh, then 1 over root 2. So yeah, uh, then again, you will operate one sigma x on here, and the other sigma x on this, and so on for the second term. And through that, you will find that it will again become something like this. Yes. Up, up. So that means when you are doing this operation, you will get plus 5. But now again, like as I said, to get the message what Alice has sent to Bob, Bob has to do these two measurements. First, acted by sigma x cross sigma x, then acted by sigma z cross sigma z, that tensor product. So then when C or when Bob measures this sigma z operator on 5 plus, you will see uh, sigma z tensor sigma z, uh, again 1 over 2 up plus down down. Then you will see that again sigma z, one sigma z will act on the first, and this second sigma z will act on second. So uh, this will this is straightforward. You can just check sigma z, 5 plus will just simply give you plus 5 plus. So that means from here, like you can you can tell that uh, uh, the after the Bob measurements, if uh, like if Bob is getting this kind of outcomes plus 5 plus and plus 5 plus, then that state uh, has to be 5 plus that L is measured. So what I'm telling, let me clear this out. Like so, like this is the exercise which you can repeat it for chi plus and chi minus as well. So let me. So like you have to do uh, two more things here. So as you 3 sigma x tensor product sigma x on uh, chi plus minus chi, and this is 4 sigma z cross sigma z 5 plus minus. So like I'm directly telling you the result right here, like how what would be the uh, final form. So, but the process to do it is this. Like, I hope you get this. When sigma x uh, x on when sigma x tensor product sigma x on 5 plus, then this is the way you add them up and you see what is the result. So this is right here. It is giving just 5 plus, and same way you do for sigma z, and then you operate sigma x cross sigma x on this time on chi plus, and again you will see like this will give you uh, plus chi. So and when you operate on sigma x on 5 minus, then that will give you. So let me uh, like tell you right here, when sigma x cross sigma x, when you operate it on 5 plus or minus, then you will get plus minus 5 plus minus. When you operate sigma x as a product sigma x on chi plus minus, then you will get plus minus chi plus minus. So you can check in the same way, like as I just showed you for one or two case. So there is no like something complicated happening right here. And for and sigma zx, you will get only plus 5 plus minus, and sigma z it's on chi plus minus, then you get minus chi plus minus. So what I'm telling, after when Alice measured her entangled pair, then when Bob measures the other pair of that entangled pair, then Bob has to do two measure. One, this sigma plus, and then sigma z. Let's say that after the measurement of Alice, Alice's outcome is, let's say, chi plus. Then when Bob measures chi plus uh, through sigma x cross sigma x and sigma z cross sigma z. Then uh, 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 like Bob will have two outcomes. One will be uh, plus chi plus, and other will be minus chi plus. So that means this will tell that uh, I mean this will let Bob to know that Alice was having this chi plus state with her. I mean after her measurement, and further he extracted two information from it, plus minus. So like as I said, using one quantum bit, like you can extract two classical bits of information. This plus is denote like some, let's say this denotes one and this denotes something zero. So you will see after when Bob, like this is what I showed you for if Alice outcome is chi plus. Let's say this is case one, and if you have another case two, and this time Alice's outcome is uh, something 5 minus, and then Bob outcome will be if 5 minus, then you can check it from here. If Bob has to first measure sigma x, that will give minus 5 minus, and then sigma z, that will give plus 5 minus. So Bob will get uh, minus 5 minus, then plus uh, 5 minus. That means again, so now the classical bits are 0 and 1. So plus denotes 1, minus denotes 0. So you can see using one entangled qubit, Alice is able to send two bits of classical information to Bob. So just what C has to do, like first we have to share the entangled qubit among this Alice and Bob. Like and first Alice has to measure her entangled qubit, and then uh, uh, after the measurement of Alice, then Bob has to do these two measurements, and after Bob does these two measurements, then Bob can like extract two classical bits of information, like you can see. So that is not possible when you are doing like when you are transmitting messages through classical bits, because when you are transmitting messages I mean when you are using entangled qubits, you can able to transfer more than one classical bits, and also it is not possible if you are using only ordinary qubits. It has to be entangled qubits. So did you get this part, like and also the operations on this
Yes. So my question is, it
uh,
is okay. So if Alice measures some, at first Alice has to measure something, or Bob has to measure something,
uh,
then or if Alice measures something,
uh,
then we know what Alice is measuring, and
hmm.
from that we can get two outputs.
Yeah, yeah. So like Alice has to like first because the entangled pair that Alice has, she is not herself aware of which entangled pair is with her. So like she has to do a measurement. So so Alice has to do a measurement, and after when she measures, then Bob has to do two measurements, and that two measurements which I was telling, sigma x tensor product sigma x and sigma z tensor product sigma z, and like as like for example, after the Alice measurement, it give so Alice measured sigma x uh, like or let's say like yeah Alice said initially chi minus, and after her measurement it gave chi plus. She must have measured we have seen here, if chi minus is there, and if you measure sigma z, so Alice has to measure sigma z, that will give chi plus. So that will give chi plus. Uh,
So
yeah,
so initially, as Alice don't know that what is the state is, that's why initially he's measuring chi minus, and
yeah,
to know that what is the state is, then he do the measurement, and he
yeah,
know now we know that it is chi plus.
yeah. Because like originally, like whichever entangled state Alice has, she won't be having any idea of which entangled state it would be.
Yes,
Any of
yes,
the four,
yes.
like it can be.
Okay,
So once she measures, she can understand based on the outcome and the operation that she does. Like she did the measurement of sigma z, and she's getting chi plus, so that she can understood that okay, like I'm getting chi plus by measuring sigma z. That means my original state before the measurement was chi minus,
okay,
and
okay.
uh, and okay, after the measurement it collapses to chi plus. And what happens then when Bob measures it, then chi plus on this chi plus, then Bob will get two bits of classical bits of information. One plus these eigenvalues are basically the information, that is the end result which you get. Like states are something uh, which is for the quantum system, that I mean the configuration of the quantum system, but the physical result are the end products that you get in form of eigenvalues. So this you will see plus for this one and minus for this one when he measures sigma x cross sigma x, and then when he measures sigma z cross sigma z, then he gets this minus. So you can interpret plus as some one and minus as zero.
Okay. So Bob
So
doesn't measure any chi minus. He only measures the state chi plus.
sorry, could you repeat again?
So after the measurement of Alice,
Uh,
Alice know that the state is chi plus.
yeah, yeah, yeah.
So now Bob will only measure two eigenvalues of chi plus.
Bob will measure sigma x tensor product sigma x, sigma z tensor product sigma
Two
z.
two eigenvalues of chi plus, not chi minus.
I mean, after the measurement of Alice, Bob has to do two measurements: sigma x tensor product sigma x and sigma z
Hmm.
cross sigma z, and corresponding to this two operators, it will give two eigenvalues. So, and that two eigenvalues will be your two bits of classical information, that which you can
Okay.
obtain it. Like that is how, like using qubits, we can transfer more number of classical bits. Uh, so that is the
Yes, yes.
advantage of having quantum entanglement. And similarly, we can have one more interesting uh, 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 use of this entanglement, and that is quantum teleportation. Now, here what happens, here you send quantum information using classical bits. So here, this is other way around. Like earlier in dense coding, which I just discussed with you right now, that is you were transmitting classical bits using qubits. I mean, you were sending your information in the form of classical bits using qubits. But now you will directly send quantum information. That means you will send your information in quantum bits, that is qubits, using classical bits. So this is like reverse of dense code. So let's say the quantum information which Alice uh, wants to send to Bob, that let's say that is psi, some quantum state. That is what Alice wants to communicate this information about psi to Bob. Then that psi uh, has to be and that psi is denoted like this, some quantum information, alpha upstate plus beta downstate. And and to do that, like how one has to do, And one more thing which uh, like there are uh, I mean, but I'm telling this site which I've written here, one way which you can say we can communicate this site, or we can transmit this site to someone else by making a copy of it. So like that, what we normally do with classical information, but you will see that that is not possible in this case, because it it goes by one theorem called uh, no cloning theorem. So so no cloning theorem says that you cannot create a copy of quantum state. So that is not allowed. So this is so therefore, one of your possible ways to do that has gone away. Like what we normally would do, we would create a copy of it, and we'll send that copy to someone which we want to which we want to deliver the message. So but now that option is also not available when you are dealing with quantum information, because you will see that you can check out some more detail of this no cloning theorem. So it's easy to prove. I can uh, if not possible, I can also discuss with you next time, since we may not have enough time to discuss this quantum teleportation. If there are more time, we will see at the end, even which I told you about this APR paradox and this Bayes inequality. You can go and check them out. If not, if you're not really finding them, I mean, not able to understand, then we can talk them next time. For sure. So yeah, the non-cloning theory avoids that kind of approach, which where you can copy the same quantum information and you can send that copy to the I mean to the receiver for the message that you want to deliver. But that is also not possible. But what can be done, let's say if this um, we again start with the APR state, so that is chi minus um, which is uh, this was given like this, and and we want to we want to send this psi, this information to the Bob. So Alice is having this entangled pair chi minus, and she wants to send this quantum information psi to Bob. Then what she has to do, uh, like uh, she has to uh, she has to involve this information, this psi information, in her entangled state, in her entangled pair state. So that is uh, psi tensor product with chi minus. So if you do this, so you can also take this as one of the exercise problem. So you have to compute this psi, the tensor product with chi minus.
Hello.
Yeah.
I just it is something like a modulation.
So it is
for
something.
for, for understanding. Suppose in electrical in signal transmission, we have seen the modulation. There is a carrier wave and there is the original wave. Something like this. The concept.
No, I mean, I I don't think it can be thought that way, because uh, uh,
Because
like there
you
is
want to
no.
transmit you no okay, I understand you, but you want to transmit the quantum state psi, but as you don't want to, you can make no clone of this state.
Mm-hmm.
So you're taking the entangled state
Yeah,
to transport the quantum state psi.
yeah, yeah, yeah.
So it is something like your original wave and the carrier wave.
Like I mean, that is very classical things. So I mean, we cannot really because I am taking tensor product. So and you're talking about some classical wave superposition. So that
Yes, yes.
that superposition is not. Uh, we
Quantum.
don't know how to see that superposition here because like in superposition in quantum states should be like you just take a linear combination of them. That is your superposition.
Okay.
But here I'm taking tensor product of that. So I mean, I don't think that is not a fair way to think about it. But like that is something very different. Like here, like we are trying to transfer quantum information, so you cannot really think of quantum information as some kind of like carrier wave, like which is classically thought of. Like I mean, I don't
Okay.
think
Okay.
there is any relation.
Okay.
Yeah. So yeah. So if you take this thing, I mean, when you do a tensor product of this psi with chi minus, you will get something alpha upstate, downstate. Sorry, upstate. Uh, let me write properly. So I have alpha upstate plus beta downstate. Uh, Tensor product. Yeah, 1 by root 2. Uh, so like I think I earlier I made a small mistake somewhere. Like the EPR state which I was calling, like I was referring to the wrong state. Actually, the EPR state is given by this one. Yeah. So yeah, this is correct. Upstate, downstate, minus upstate, minus downstate, upstate, and so this one which I was referring here. So that is not your EPR state. So uh, I mean, so yeah, sorry for that. Uh, Upstate, downstate. Sorry again. So this is yeah, up down minus down up here. Right. That is your EPR. So yeah. So in here again, up down is down up. So you have to take this. So when I do this computation, so I will get here uh, 1 over root 2 the common factor. So alpha upstate, upstate, downstate minus alpha upstate, downstate, upstate, then plus beta, downstate, upstate, downstate, minus beta, downstate, downstate, and upstate. And you will see that like I can further uh, uh, here what I can do like I can take common factors of let me also remind you, we also had 5 plus as, so 1 by root 2 upstate upstate minus downstate downstate, and 5 minus like uh, so this is 5 plus 5 minus would be same state, but there will be minus sign here, and then chi plus same as APR, but with positive sign. Uh, so so using this, like I can write in a factorized form where I can do what, like uh, so like you have to use this, and in that factorized form, like I'm directly writing it over here, so that will give you alpha 5 plus 5 minus uh, minus so yeah, I took a common factor from the first two. Similarly, I can uh, write a common factor of minus alpha uh, chi plus chi minus upstate plus beta uh, chi plus minus chi minus. So okay, so uh, so that means or I can rearrange this bit, that will give me 5 plus 5 plus, then that will be minus beta upstate plus alpha downstate, then plus 5 minus beta upstate plus alpha downstate, then again I have plus chi plus minus alpha upstate plus beta downstate minus chi minus alpha upstate plus beta downstate. So yeah, so that is your final form when you take your uh, quantum, when you take your entangled qubit tensor product uh, with your qubit, which you want to send this information to Bob. So this is what like Alice has to do this. I mean, this is what Alice is having. This as your uh, information with her, and then she wants to send it to Bob. Then the next, what Alice has to do now, um, just like wait a minute. So this is uh, let me check states of code. Alpha plus, okay. Okay, like, did you get this competition right?
Yes, I have to check later.
Okay, so I have skipped like one more step like in between because like I wanted to solve it quickly, but like you have to after when you do this tensor product, then I have to I mean basically you have to use this uh, forms of chi plus, phi minus, phi plus, and chi plus, and using them like you can get it. Like for example, uh, the state which I have written, uh, uh, this state, like you can get it by taking a sum of phi plus, phi minus. So same way like this uh, up down states, that you can get it by taking the I mean by this combination. So like that, like I've taken. So I've taken up state is some this phi plus phi minus, and up down state is chi plus chi minus state, and same way like down up state is this, and down state is this. So that is what I've done. So nothing like drastically something new I'm doing here. So I hope like you get this one, right?
Yes,
Okay. So yeah, like when you do this, like you have this state. So Alice right now has this entangled state. I mean, not the entangled state. Like it is the tensor product of the qubit, which she wants to send it to Bob with the entangled state. Now, like again, like you will see that there are many entangled states in this linear combination of state. Like there is this phi plus, phi minus, chi minus, chi plus. Well, exactly again, she doesn't have any idea of which state like she has. Again, just like before, when we were doing dense coding, like we said, like Alice has entangled pair, but she doesn't have any idea which entangled pair it is. She first has to do some kind of measurement to know which entangled pair she is possessing. And so again in the same case here, like I mean uh, in this time also, like Alice cannot know without measuring which state like she's in. Let's say she does a measurement and she gets Alice uh, measures 5 plus. Then if she measures 5 plus, uh, then then she has to tell Bob that, or then Bob has to measure, Bob has to measure sigma y uh, on his qubit. That is, uh, when you operate sigma y on minus beta, then that will give like when sigma y acts on. So when sigma y acts on upstate, then that gives minus I downstate, and then sigma x on downstate, that gives I upstate. So using that, like I will have uh, I beta downstate uh, plus I alpha upstate. So that means this is I psi. So 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 this is when Alice measures 5 plus, then Bob has to measure sigma y. and when he measures sigma y, then it is like what Alice wanted to send to Bob, that psi, this psi has been communicated between Alice and Bob. So like, did you get like what I'm trying to say here?
So what you are saying is that after the tensor product,
Yeah, after the tensor product.
tensor
So
product,
so this is
now
the
you
this is the
now
state, the tensor product
state.
state, which
So
this one, this is now prepared in this
prefer.
final form.
Now, if Bob wants to know the quantum
Uh,
information, then he have to operate sigma y
huh.
and code the
But before measuring Bob, Alice has to do the measurement, because Alice has this state, this tensor product state, this psi chi minus. Alice has this state. There is no problem. Uh, this is the state Alice has, but uh, Alice has to measure this state. I mean, she doesn't know what is the state is exactly. Just like before also, even if you have any entangled state, you don't know which entangled pair it would be. So now, if Alice has this state, then Alice doesn't have any idea which state it exactly is. So Alice has to measure this state, and upon measurement, let's say she's getting 5 plus, and she's getting 5 plus, and with that 5 plus, she would also have this state attached to it.
yes.
So if when Alice is measuring this psi tensor product with chi minus, it collapses to this first term, this first term. And when it collapses to the first term, so that means she's getting 5 plus state, and then she informs Bob to measure sigma y. So when she informs Bob to measure sigma y, then when Bob will measure sigma will act on this. So this is again tensor product. Remember, let me let's say this state. I'm denoting this state as one as 5 plus, uh, then uh, minus beta, tensor product with minus beta upstate plus alpha downstate. So Bob now will measure uh, sigma y. So this sigma y, when Bob will measure on this sigma y, that means it will uh, Bob has to do this measurement, identity sigma y uh, on 5 plus then tensor product of this step. This is this. So when Bob measures, that is uh, yeah. So that is sigma y when Bob measures, uh, like Bob is getting this. So uh, like if Bob measures something sigma x sigma y, then exactly you won't get this sign. So now what happens? Like if Alice measures 5 minus, then that means after the measurement of Alice, that entire state collapsed to this term. Let's say this is something 2, and then uh, Bob has to measure something that from there it like Bob will get this state. So that means if Alice is getting 5 minus, then Bob has to measure sigma x. Then Bob has to measure sigma x on his qubit. That is sigma x when x on uh, sigma x when it will act on uh, sorry, yeah, sigma x will reflect on beta upstate plus alpha downstate. Then again, when sigma x acts on upstate, it will give downstate, so it will be beta downstate plus alpha upstate. Then this is your psi. So again, Bob gets this information about sign. That is the information which Alice wants to send it to Bob. So that is how you transfer your quantum information. That this is your uh, phenomena of quantum teleportation, which you transfer your quantum information. Uh, yeah, is it now like
So
yeah?
yes, I
Did you
understand it.
get this?
But yes, yes. So LS can also measure chi plus or chi minus state. But then which operator has to act on the product state of chi plus,
Uh,
and then the
yeah, Alice has to measure. Yeah, if Alice, like after the measurement of Alice, if she is getting chi plus, Alice, let's say Alice measures chi plus, then Bob has to measure. Uh, then Bob has to measure, like in chi plus you have minus alpha up, and so in that case, Bob has to measure sigma z. I think yeah, sigma z. If uh, so, then Bob has to measure sigma z on his qubit. So what it will give sigma z on minus alpha upstate uh, plus beta downstate. So that will give when sigma z x on upstate, then it will simply upstate. But when it x on downstate, then it gets minus downstate. So that is minus sign. So this is uh, what Bob has to do. If Alice gets chi plus, then Bob has to measure sigma.
but
So
now he gets a negative eigen value minus
yeah,
one.
negative
Is it
sign.
okay?
Yeah, I mean, Bob is able to get the information up to a some phase. So like that negative sign is some phase. So like I can
Okay.
write something as something e to the power I pi psi something like this. And also even before at the beginning, like this is iota psi. Again, iota is again some phi. I mean some phase. So
So if I consider that it is a state on a circle, the psi is a state on a circle, so it is getting some another point on the sphere,
uh,
but not on the exact sphere. The same thing, but in different position.
yeah, yeah, you can say that yeah, even right, yeah, the same thing, but you can able to get the information, but up to some phase vector. Like you can
Yes,
say it is
yes,
like something you can toggle through a sphere or like a block sphere if you
yes, yes.
want to use it. Like if you are really looking for that term, then yeah, that is something on block sphere. So
Yes, yes.
so yeah, that is about the like quantum teleportation. So I hope this is clear or anything more.
Uh, it's clear. I think this lecture is very nice because the output is very simple, but the calculation is you have to know what you want to get.
Yeah.
And then output is because in the last lecture when you are doing calculation, the
Ah,
calculation is very big.
right,
But
right, yeah.
here, but the calculation is okay, but you
Ah,
have to technically
ah.
think that which study you want to get.
Mm. Yeah, here you need a lot of this. I mean, technical thoughts you need to understand. You need to like I mean, you need to basically deal with the technical ideas, but not rather through rigorous calculation, unlike
Yes.
like the last time. Yeah. So yeah. So like, there's any more thing, or like as I was telling about this EPR or no cloning theorem, like I can discuss with that maybe next time, or if possible, like
Okay. Okay.
whenever,
Okay.
like
Okay.
if you are having
So
doubt, like I
I
can.
just want to know that you have only one lectures for quantum computation, yes? Because
Uh,
in the next lecture, you are going some the schedule I saw is something time dependent perturbation, something
Yeah,
like
yeah,
this.
yeah. Last time I talked about some, yeah, time dependent emitter. Yeah, I think even in next week there is this time dependent perturbations are there.
But quantum computation is not more there.
Probably not, like
Okay.
because I really don't have that idea, like how this core structure is designed. So, but like, yeah, you can check the I mean uh, the outline, or I mean the syllabus of this course. Uh,
Only
the
one lecture for quantum computation.
yeah,
Nothing.
yeah, yeah. So even if there is some more topics, if that would be like taught in this like lectures, then I will definitely catch up to that, like there is no issue. So yeah, I will talk on to the topics which is being covered, and also if there is something like you find missing, or something you wanted to have an idea about something more, or something like it's not really able to I mean, not you are able to get it, like you can ask it anytime, like during our this like tutorial
Okay.
sessions, we can
Okay.
talk about it.
Okay. Thank you.
Okay, if there's normal, then we can like end it right here. I think we are also cover the time, so we can meet again.
Okay. Thank you.
Okay, yeah, bye.
Bye.